Hello and welcome to curve sketching. I've been talking about it for the last few weeks. We're finally here. Today's notes, I'm going to go through it pretty quickly because it's everything we've been learning the last 2 weeks. We've learned the steps along the way, and then now we can just put them together and do curve sketching. And yes, we are actually graphing. Today we'll look at graphing polynomials, and next lesson we'll look at rational functions where we have some asymptotes. But today there's no asymptotes, polynomial functions. We already did this topic in grade 12. We graphed polynomials, we graphed rationals. So it's the same topic, but we're doing it with a little bit more detail, and we're supporting our results using calculus and sign diagrams and limits and derivatives. Instead of just memorizing those rules about why we have asymptotes, where we have them, now we have to show why and with supporting work. So I know we've graphed them, but a little bit more detail with a little bit more backing our knowledge about why the graph looks the way it is. Okay, so very simply today, so we're doing polynomial functions, so no asymptotes today. So the steps: determine the first derivative and the second derivative. Then you make a sign diagram for the first derivative, and that's where you get your min-max values. Then you make a sign diagram for the second derivative. That's how you get your concavity and inflection points. And then you do need to solve for the corresponding y values for all of these. It doesn't matter what order you do it. I like to do them all together as one, but you can do these first, then get the corresponding y values. And then you plot your extrema, plot your min-max points and your inflection points. And then you connect them with the smooth curve. Remember, these are continuous functions, and these are polynomial function graphs. So a smooth curve with proper concavity. No asymptotes today, so just kind of putting the pieces together. Okay, so one example we'll do together. So the initial function, we have x cubed minus 9x squared plus 15x. We know from pre-cal 40s how to draw cubic functions. We know what the end behavior looks like, right? So we can connect some of our knowledge from grade 12 pre-cal, so we should already be able to visualize what the general shape looks like, which way the arms, the end behavior is going. So think back to grade 12 pre-cal, so you are starting with some kind of frame of reference. Okay, step number 1, we get the first derivative, which I already did for you. Then we set it equal to 0, and you should realize you can factor out a 3. If you didn't realize that, you would notice that later on. And then we use this to make our sign diagram, or we can factor this even further. So we have minus 5, minus 1. So we have two critical numbers. The critical numbers would be 5 and 1. We make our sign diagram, 1, 5. We take a large number, a million, run it through, and make our sign diagram. I'm going through this quickly because this should be really easy for you. Okay, so this is our sign diagram for the first derivative, and this is where we get our min and max values. So we look, we go from positive to negative. Oh, we know that that would give us a max value. So we have a max where x equals 1. We're going from decreasing to increasing, so we'd have a min. So we have a max at x equals 1 and a min at x equals 5. And then the next page, I started it, so we have a max at x equals 1 and min at x equals 5. Before I go to the second derivative, I'm actually going to solve for the corresponding y values now, just because I like to keep all that information together. So I already did it for you. I remember we go back to the original function. You don't plug it into the first derivative. You plug these into the original function. So when x equals 1, you get a y value of 7. So when we plot our graph, we're going to have a maximum point at the point 1, 7. Then we take our min value, x equals 5, plug it into the original function, not the first derivative. I've done that correctly. I should get a value of negative 25. So that means when we make our graph, we have a minimum at the point 5, negative 25. Okay, let's keep going. We're about a third of the way through the question. Then we get our second derivative, and then we set our second derivative equal to 0, and we should realize we can factor out a 6. Then we make our sign diagram for the second derivative. Run through a million. There we go. That's our sign diagram for the second derivative. Now, what kind of information does the second derivative give us? That gives us concavity and inflection points. So from minus infinity to 0, our graph will be going concave down, and from 3 to infinity, it will be concave up, and we will have an inflection point at x equals 3 where it changes. So we need to find the corresponding y value, so I think I set it up here. Yeah. So we know we have an inflection point when x equals 3. Again, plug that back to the original function, not the second derivative. So when I plug that in, I should get negative 9. So now I know I have an inflection point at 3, negative 9. Now here's an extra one. I didn't talk about a test point. You don't have to do that, but sometimes it's good to do. The more information you have, just the more accurate your graphs will be. I just use x equals 0 because it's nice to know what happens right there. So again, when you run it through, it goes through 0. So we know that the graph goes to the point 0, 0. That's not a min, that's not a max, that's not an inflection point, just an easy point to get to kind of help get the overall shape of our graph correct. Okay, so that's what we've been doing the last 2 weeks, and we did have to graph. Now we're going to put it together and graph it as best as we can. I'm not a very good grapher, as you know, so I'll do the best I can. Again, we are doing this without technology. Sorry, no Desmos and calculus. So where do we start? I know that it goes to the point 0, 0. I know that, we'll pretend that I have graph paper, we'll pretend I have a scale. I know that I have a maximum value at 1, 7. I have a minimum value at 5, negative 25. Well, we'll see how this turns out. And I have an inflection point at 3, negative 9. Okay, so like I said, we know that goes through 0, 0. That's our inflection point. That's our min-max values. And then according to our graph, we know that it is going to be going concave down from 0 to 3. Or minus infinity to 3. So it's going to come like, oh, perfect. So that would be the concave down part of the graph. So that matches our second derivative sign diagram. It's concave down from minus infinity to 3. Then it's going to be concave up from 3 to infinity. And then concave up 3 to infinity. And then that's not bad. It should be one smooth curve. The fact that I stopped midway, you don't want to make breaks in it, but that matches. So our first derivative tells us that it's increasing, decreasing, increasing. Yeah, that matches our sign diagram for our first derivative. Our second derivative tells us it's concave down, concave up. Yeah, we have an inflection point here. Yeah, and got our min and max, and that's our graph. So today's assignment shouldn't be that bad. We're just putting them together and to get polynomial graphs. Make sure you complete this because next lesson it's the same thing, but we're going to have asymptotes. So it's the same idea, but we're going to have extra steps. We're going to have to do our limits at infinity to infinity and use our rules to figure out where the horizontal asymptote, vertical asymptotes are, in addition to min, max, concavity, and inflection points. So it's long and tedious, but like I said, if you can do one question of curve sketching, that means for the most part you've understood pretty much everything we've done so far in calculus. Okay, so have fun graphing the polynomial functions today.